Okay, so in the interest of time, we're going to go ahead and get started. Hope everyone's got plenty of blood sugar in them and is ready for some really good talks. The first one of the afternoon session is from Dr. Tom Isabell from JEOL. He is the Vice President of Product Management at JEOL USA. And since joining JEOL in 2004 as Assistant TM Product Manager, he's been working with the JEOL USA TM group in Japan and with the customers to make sure that they are at the forefront of TM technology. He's going to tell us all about it. Take it away, Tom.
Fantastic, thanks. Thanks again to you all for organizing this and for inviting us and having us here. So what I'm going to do today is go through using advanced electron microscopy for characterization of 2D materials and quantum materials. So what really are our objectives with this? Certainly we've got to determine the structure with imaging, so either TEM or STEM. The chemistry we want to know. We can use chemical techniques like EDS or EOLs to figure that out. Good to determine the electrical magnetic properties, domain structure, ideally do it in situ if we can. What are the concerns with doing this? You know, trying to get the structure and trying to do the imaging, worry about beam sensitivity. A lot of these materials, will just blow apart. Chemistry, beam sensitivity. How can you get enough signal for EDS or EOLs or for the characterization techniques before you destroy the sample? And then the electrical magnetic properties, again, beam sensitivity. But what technique? There's a lot of different choices. We can do Lorentz TEM, STEM, Lorentz STEM, various STEM techniques. Is in situ possible? So for beam sensitive materials, it's increasingly important to monitor and control our dose and to collect analytical information without modifying the sample. So what are our options? Well, we can lower the KV and drop below the knock-on threshold for most materials. For simple carbon, for example, that's 77 kV. We can decrease the dose, or we can maximize the imaging and analytical efficiency through advanced detectors, advanced systems, but we still need to obtain the desired results that we want to get. So our resolution is going to be degraded by chromatic aberration effects that are more dominant at lower voltage. So if we drop the KV, we're going to worry about that. And our dose must be sufficient enough to generate the signals that we want. So our solutions for lowering the KV, we can retain some of the resolution by aberration correction. You heard a bit about that already this morning. And also by using a cold field emission source. That will help us minimize some of the other aberrations as we change and correct out the CS. This helps us retain our spatial resolution. Decreasing the dose. We can do this by dose modulation. We can do beam blanking, electrostatically or otherwise, to really minimize the number of electrons hitting the sample at a given time. It's very much on the fly, and it can be done with no loss in inherent resolution. And we can maximize the imaging and analytical efficiency. We can do this through new STEM detection methods, or larger, more efficient EDS systems, for example, various ways of doing that. So we're going to lower the KV. When we lower the KV, I said one of the ways to minimize the other effects that creep in, like chromatic aberration, is by using a cold field emission source. So if we go ahead and plot out our diffraction limit and our chromatic aberration effects in a plot of beam diameter versus your convergence angle, kind of the sweet spot in between the two of those is really the beam you want to use. So if we do it with a Schottky with a larger energy loss or a larger energy spread, we're kind of right down around this regime. If we use a cold field emission gun, it's got a smaller delta E, this delta E over E factor here. It lays this curve here, or this beam, this line flat, gives us this larger range. So basically it means we can use smaller probes. We're down to a much smaller probe size, but a larger convergence angle, which means we can use larger apertures so we get more probe current. So we get the best of both worlds. So this is just a comparison of the two. This is on a cold field emission source system, but just comparing two different energy resolutions. So again, really just comparing the chromatic aberration effect between the two. So at 0.4 EV, we've lost the ability to split the dumbbells. At 0.3, we can. Just some other examples of low KV imaging. Carbon at 80 kV, silicon down to 30, gallium nitride 110, and other 2D materials. So just by dropping the kV, we can minimize the damage as much as possible and get back some of these effects. Some other quick examples to go through. Moly disulfide, again, imaged at 80 kV. Get these different, two different structures. And being a high angular dark field, it's sensitive to Z. You can see where there's a pileup, or not just two moly-on-moly atoms. We can do this with tungsten disulfide. Actually imaging it, this is obviously a quick movie. You can see the single atom moving around. These are obviously still shots as you go through, and you can see the point at which, again, you've got an atom on top of an atom. So a thicker regime, you get more contrast. We could take that same material and do the chemistry of it. So just our straight images that we were just showing, plus EDS. So using large angle EDS systems, I'm not going to go into details. There's a number of different systems out there that can be used now. But we can, again, do this on an atomic level, do this without degrading the sample. All right. How about decreasing the dose? What can we do? So we can use electrostatic dose modulation. In this case, literally, and it's an electrostatic shutter that allows us to cycle the beam on and off, pixel by pixel, in a very, very controlled fashion. It's very much on-the-fly dose control without affecting the imaging conditions at all. And we can then synchronize this with timing control with the STEM system, for example, to really do true temporal dose structuring. We can do dose painting. We can determine when and where we are going to apply how much probe current on any given spot on the sample. We can use that in feedback systems. We can do AI with that, determine that we want to do more dose here, less dose there. And if we want to do time resolved sorts of experiments, we can time it out with a laser probe, for example. Hit the sample with a laser and time it such that we image at right around then and in increasing cycles. This is an example of doing exactly this. So this is basically starting at 90% duty cycle, so almost 100% full beam. This is a single image. This is not images that are stitched together or stacked together. That's taking, as we're doing the STEM scan, and using the dose modulation system to turn the beam down from 90% duty cycle to 10 and back up to 90. All within a single image. You can see it doesn't drift. There's no loss of resolution. We're just controlling the actual dose that's hitting the sample. As I said, we can then go through and synchronize this with control systems. We can go in and use a very simple dose painter sort of thing. I mean, this is just like Microsoft Paint. Go in, you have your reference image back here. Go in and draw any sort of shapes you want, and within each of those shapes, you can choose and select the duty cycle you want. Therefore, you can select how much the beam is on for each different region. The bright white is 100% duty cycle, the black is 0. So if you go back and scan again after this has been masked, those are the images you get, bright field and dark field images. So again, just showing those exact boxes and shapes and circles and whatever you drew. Again, the black shows up as black because the beam was never on those pixels. It was the 100% was on the largest square region, but the black all the way around is nothing. We could take that a step further. Again, just a regular scan of just these gold particles on carbon. And instead of drawing different shapes and using a dose painter sort of system with it, we can load in an image. So you can have a preloaded dose map, if you will, that you would like to have. We can use this as a mask. So this image of a microscope actually, these fractal patterns, the logos on the top. And then if we go through and take the image, that's what we get. So we've gone through and recycled the image. We've got the gold on carbon again. Again, the contrast differences you see in is because the beam was on more in the brighter spots, it was on not at all in the dark. If you zoom in on this area over here, you can see there's this fractal pattern that was done. If you zoom in even further with it, it's this full checkerboard. And you can see in each of those positions where the beam was literally going on and off as it was going across and scanning. So to really take this to the extreme, you can take this and feed this back through, do some analysis, do some real AI learning, take that initial scan pattern, load whatever sort of initial exposure pattern you have, get the image, analyze it, depending again on what you're trying to look for and do, apply any AI, generate another exposure pattern and repeat this loop until you've got what you're looking for to analyze the data. So again, lastly, we can maximize our imaging and analytical efficiency through new detectors, so kind of normal STEM detection methods, annular dark field, which is Z contrast, so heavier elements show up brighter. Bright field, very similar, very close to conventional TEM, not straightforward. Annular bright field is enhanced contrast for lighter elements. You've got segmented detectors, pixelated detectors, and I'll talk more in detail about these. The standard detectors, the three in the blue, the ADF, the bright field, and the ABF are really the detectors that you're used to seeing on a microscope, insert, retract. They are all integrated signals. You're getting everything that hits every part of that detector. The segmented detector and the pixelated you can control. You can get what you want from various parts of those detectors to create various signals. Again, normal kind of standard STEM detectors, annular dark field detector, small and your bright field. Again, kind of the normal, what you're used to sort of detector STEM images. A pixelated detector, we can do full four-dimensional STEM. So at each pixel across the pixelated detector, we can get a full diffraction pattern. We can then go back post-processing wise and analyze that, mask that series of diffraction patterns, do whatever you'd like, pull out a bright field image, pull out a dark field image, or more complex things. There are segmented detectors, which are exactly what they sound like. In this case, this is an 8-segmented detector. And you can read out each segment individually. So what this allows you to do are, again, various things. You can get the signal from each segment independently. You can do mathematical functions within each segment or to the segments, add them together, subtract them apart. One of the things we can do is what we call OBF STEM. It's optimum bright field STEM. And what it does is it helps us maximize our signal to noise. It's very good for very low dose. So going back to what I was talking about minimizing the dose on your sample. Light element detection, because you were maximizing the signal to noise again. And it's fast, it's live. So what it is it's using, again, this segmented detector. What we're doing is we're calculating the phase contrast transfer function for each of the segments within the detector independently. So the images from each segment are then combined using a very complex frequency filter, again, based on this phase contrast transfer function to obtain the highest signal to noise for each segment, for each section. So the OBF is really effective real-time imaging for very good beam-sensitive samples. So you can think of it, it's an imaging filter. So you can compare it to just a straight low-pass filter that you'd use for normal sort of image manipulation. Very much the same idea, but instead of just a straight low-pass filter where you do the entire image all at once, in this case we've got the 4 different segments, do the transform, mask it, do the inverse transform with the summing and the other mathematical functions to it, and recreate the image, get it all put back together. If you want to dig into the heavy-duty math that's all behind it, this is the reference, this OA ultramicroscopy paper from a few years ago. But since we're doing this per segment and we're optimizing the signal to noise across everything, when we put the images back together, they're, again, very much kind of more independent of Z and much more dose independent as well. So the top, is an annular bright field image, so that's going to bring out your lighter elements and pop your lighter elements. The bottom are these OBF images. What I want you to notice are the beam currents as we're going all the way down to 1/10 of a picoamp all the way at the right. Very, very, very low dose. The ABF image barely even shows up, but we do the recorrection of the optimal bright field, and it looks almost no different than with the higher probe currents. So this allows us to go back to some of these 2D materials and some of these very beam-sensitive materials and image them with very strong, very high signal to noise. So this is a MOF, for example, and a zeolite, which should typically be beam damaged very, very quickly. But we can image them using this OBF technique. And again, it's a live technique. It's not a post-processing, have to wait for everything to go. Another thing that we can do with these segmented detectors is DPC, differential phase contrast. In this regard, it's a good way to measure electrical or magnetic fields within your sample. As you're scanning the beam across, if there is I can't see this much, a magnetic field or an electric field, it's going to deflect the beam at each pixel. And by deflecting that beam, if you've got a segmented detector down below, the segments where the beam is deflected to are going to register higher than the ones that don't. So if you go back through, you can then, from that, calculate and tell what the local magnetic or electric field is. So we can do this and go through, measure, in this case, a PN junction. We can see the domain between the two. But it really can be done with an aberration-corrected type of machine and system like that. It can be done on a true atomic level. As shown in the top right, you can see these skyrmions that have been imaged using a system like this. So to take that little step a little further, I mentioned at the beginning, for these kinds of materials, wanting to know what we can about the electric and magnetic fields. We can do that with Lorentz, TEM, or STEM, where you just minimize the fields in and around the sample, typically in the objective lens, or you have a special objective lens that minimizes the fields at the sample. The problem with that is how minimized is minimized. And more so the problem with that is when you're doing that and you're shutting the lenses off, you're killing your resolution on your microscope. So we can do DPC like I just showed, but again, how minimized is your field? So what if we can do all of this in a true field-free environment? So to that end, there's a system that's been built at the University of Tokyo in conjunction with us called MARS, Magnetic Field-Free Atomic Resolution System. In a typical TEM, you've got your sample sits in the middle of your pole piece. That's where you've got the largest field. So your sample is going to be affected by the field from the pole piece itself. In a MARS system, we have an upper and a lower pole piece that cancel each other out at the sample level. So it's a truly field-free environment right at the sample. This is just a map of what the fields are. Right at the very center of the sample plane and at the center of the sample itself, we're less than 0.2 of a millitesla of field. So we can then go through, measure local fields or apply fields and see what happens in a true field-free environment. This is just showing TEM imaging. Just showing a sample of gold, that you don't lose the resolution of the microscope by having this pole piece design. This is, on the right, that's an image of iron put in a typical TEM. So normally you would have such vast astigmatism and beam deflection that you wouldn't be able to image. We can do TEM in addition to the STEM like those images were. We can do bright field, dark field TEM. This is an example of, again, iron. Just looking at dislocation movements in dark field STEM. This is, for those of us old enough to have done it, good old two-beam condition, dark field STEM dislocation movement. Taking it again to that atomic resolution kind of level. Was the last example. I think this movie should be going. This is the STEM reconstruction. So this is see the magnetic domain. This is now in this kind of helical structure, kind of going in and out of the plane. Now we started to apply a field perpendicular to the plane, and the domains change to a series of skyrmions. And you can see as the field gets too high, they disappear again. And then we start to bring the field back down. They return. And then once you go through the 0 point, the zero field point, they'll go back again to this helical structure. And then as you go back through and apply the field in the opposite direction, the skyrmions will reappear, but they're inverted. The field directions are completely changed. So with that, I'll zip through And just with that, I'll finish up real quick. So, we can minimize the doses. We can minimize any of the sample damage that we see, and we can then apply all of that together and look at these electric and magnetic fields in these sorts of materials. So, thanks.
All right, thank you, Tom. We have time for one quick question. Anybody got a quick question?
How many of these techniques are things that we can access on the tool set that we have in-house? How many are sort of software related, and how many require either new accessories or a whole new column? And
So the dose control, all of the dose control stuff that I showed you is all really software related. Or it can be modifiable. It can be done on the systems you've got here. The extreme detectors, the segmented detectors, things like that, again, could be added to your system. That's hardware. The final and the Mars, the magnetic field pole piece, that's a separate instrument entirely. But most of the first couple can be modified and added on, retrofit.
All right, thank you very much.
All right.